Hello viewers, today in this program I will explain you an important application of the differential calculus, that is minima or maxima of a function f x y is equal to 0. Here, if a function f x y be a function of two independent variable and it is continuous and finite for values of these variables in some neighborhood of the point a b, then the function is said to have a maximum at a b if f x y is less than f a b for all x y in the neighborhood of a b and x y is not equal to a b. Similarly, the function is said to have a minimum at a b if f x y greater than f a b for all x y in the neighborhood of a b and x y is not equal to a b. To find the point a b for which the function f x y attains a maximum or a minimum, expand the function by Taylor theorem. For the function of two variable, that is, the Taylor theorem is expanded as follows: f x plus h comma y plus k is equal to f x comma y plus h f x plus k f y plus and so on, second order derivatives also. For sufficiently small h k, the first degree term h f x plus k f y govern the sign of right hand side of the expansion. It is clear that the sign of left hand side will change with the change of sign of h and k. Thus, for the maximum or the minimum of the function f x y, we must have h f x plus k f y is equal to 0. But since h and k are independent, we must have f x is equal to 0 and f y is equal to 0 separately. This equation form a set of necessary condition for a maximum or a minimum of the function. However, it should be noted that these equations are not sufficient. Further tests have to be employed to make the conclusion about the minima or maxima. Now I will explain you how a critical or saddle point is generated. The critical point. A point a b is said to be critical point of the function f x y if f a b is equal to 0, implied del f over del x at a b is equal to 0 and del f over del y at a b is equal to 0. The figure a and b in the next slide show the critical point for the function f x y. Figure a shows the critical point when the function attains minimum at the point a b. Similarly, figure b shows the critical point when a function is maximum at the point p a b. In the figure a, critical point when the function has a minimum at the point, and figure b, critical point when the function has maximum at the point a b as shown. Now, the saddle point. Critical point a b of a function f x y is said to be saddle point if f x y has neither a maxima nor a minima at the point a b. I will explain the Lagrange condition for the minima maxima of the function of two or more variable if a condition is given. If f x y has a maximum or minimum at a b, then del f over del x is equal to 0, del f over del y is equal to 0. Also, if del 2 f over del x square at the point a b is equal to r, del 2 f upon del x del y at the point AB is equal to S and del 2 f over del y square at the point AB is equal to T, then f of a plus h comma b plus k minus f of AB, that is change in the function, is equal to half r h square plus 2 s h k plus t k square plus r 3, where r 3 stands for terms containing third and higher degree terms of h and k. Thus, when h and k are sufficiently small, the sign of the right hand side of the equation governed by the sign of r h square plus 2 s h k plus t k square. Therefore, if r h square plus 2 s h k plus t k square is negative for all such values of h and k, then we have a maximum at AB. On the other hand, if r h square plus 2 s h k plus t k square is positive for all such values of h and k, then we have minimum at AB. Now, we can write r h square plus 2 s h k plus t k square is equal to 1 upon r h plus s k whole square plus k square upon r t minus s square. Therefore, r h square plus 2 s h k plus t k square is invariably negative if r is negative and r t is greater than s square, and r h square plus 2 s h k plus t k square is invariably positive if r is positive and r t is greater than s square. Thus, f x y has a maximum at AB if r is negative and r t is greater than equal to s square. It has minimum at AB if r is positive and r t is greater than s square. But if r t is less than s square, f x y has neither a maxima nor a maxima. If r t is less than s square, f x y has neither a maxima nor a minima at the point. When r t is equal to s square, we need further investigation to find if the function has an optimum point at the point A B. For example, consider the function f x y is equal to 20x plus 40y minus x square plus 4xy minus 2y square. Taking the first order partial derivatives, we have del f over del x is equal to 20 minus 2x plus 4y and del f over del y is equal to 40 minus 4x plus 4y. Taking the second order partial derivatives of f x y, we have delta 2 f over del x square, that is equal to r, which is equal to minus 2, and del 2 over del x del y equal to s, that is equal to 4, and del 2 f over del y square equal to t, that is equal to minus 4. Now, putting the first order derivative del f over del x to 0 and del f over del y equal to 0, it gives 20 minus 2x plus 4y is equal to 0 and 40 minus 4x plus 4y is equal to 0 respectively. Solving these two equations, we find x is equal to minus 30 and y is equal to minus 20. Thus, the function has a critical point at minus 30 minus 20. Now, at the point minus 30 minus 20, RT minus s square is given by minus 8, that is less than 0. Hence, minus 30 minus 20 is saddle point of the function. It has no minima, no maxima at the point A B, that is minus 30 minus 20. Now, I will explain you a Lagrangian multiplier method for minima and maxima. This method is applicable when we are to find minimum or maximum point of a function of two or more variable with a condition. Condition may be repeated condition, may be double or triple condition. We have the method as follows. Let u is a function of several variable, that is n variable function f x1 x2 dash 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 xn be a function as defined earlier of n variables. M constants and only n minus m independent variables are there. The function u has maximum or minimum at the point x1 x2 dash 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 xn if the first order partial derivative du is equal to del f over del x1 dx1 plus del f over del x2 dx2 plus and so on up to del f over del xn dxn is equal to 0. Also df1 is equal to del f1 over del x1 dx1 plus del f1 over del x2 dx2 plus and so on up to del fn over del xn dxn. Similarly, df2 is del f2 over del x1 dx1 plus del f2 over del x2 dx2 plus and so on up to del f2 over del xn dxn. In similar manner, dfm is equal to del fm upon del x1 dx1 plus del fm over del x2 dx2 plus and so on up to del fm over del xn dxn is equal to 0. Multiplying these equations with 1 lambda 2 dash 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 up to lambda m respectively and then adding all the results, we get p1 dx1 plus p2 dx2 plus p3 dx3 and so on pn dxn is equal to 0, where pr is equal to delta f over delta xr plus lambda 1 delta f1 over delta xr plus lambda 2 delta f2 upon delta xr and so on up to lambda m delta fm upon delta xr for the values of r 1, 2, 3 and so on up to n. The quantities lambda 1, lambda 2 and so on up to lambda m are arbitrary constants. Hence, here are chosen that pr is equal to 0 for r is equal to 1, 2 dash 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 m. The above equation now reduced to pm plus 1 dx m plus 1 plus pm plus 2 dx m plus 2 and so on up to pn dxn is equal to 0. It does not matter which m minus n of the n variable are considered as independent variables. So, assume that x m plus 1, x m plus 2 and so on x n are independent variables. Since dx m plus 1, dx m plus 2 and so on dx n are all independent, the coefficients p m plus 1, p m plus 2 and so on p n must separately be 0. Thus, we obtained a set of additional n minus m equations p m plus 1, p m plus 2 and so on p n is equal to 0 separately. From these m plus n equations, we find f x 1 is equal to f 2 is equal to and so on f m, the all functional value is equal to 0 and also p 1 is equal to p 2 and up to p m is equal to p m plus 1 and up to p n all are equal to 0. We can determine m quantities lambda 1, lambda 2 dash 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 lambda m and the values of n variables for which maxima and minima value of the function u f x1, x2, xn are possible. These coefficients lambda can be obtained from by solving these equations. For example, find the optimum value of the function f x y is equal to x square minus 3xy plus 12x. This is two variable function subject to condition 2x plus 3y is equal to 6. So, we will apply to find the minima maxima of this function under the condition we apply the Lagrangian rule. Therefore, we form a Lagrangian function L is equal to x square minus 3xy plus 12x plus lambda times the condition as 6 minus 2x minus 3y. Taking partial derivatives of this Lagrangian function and equate them to 0, we find del L over del x is equal to 2x minus 3y plus 12 minus 2 lambda is equal to 0. Del L over del y is equal to minus 3y minus 3 lambda is equal to 0, and del L over del lambda is equal to 6 minus 2x minus 3y is equal to 0. Eliminating y from equation 1 and equation 3, we get 4x minus 2 lambda plus 6 is equal to 0, that is equation 4. Similarly, solving equation 1 and 4 now, we have lambda is equal to 1 and x is equal to minus 1. Putting this value of lambda and x in 1, we find y is equal to 8 by 3. Thus, the function f x y is equal to x square minus 3xy plus 12x subject to condition 2x plus 3y is equal to 6 has an optimum value when x is equal to minus 1 and y is equal to 8 by 3. Today in this program, I have explained an important application of the differential calculus, that is minima maxima. Actually, we have discussed the minima maxima of a function of two or more variables. I have explained the terms saddle point, critical point and point of inflection also. The necessary condition for a function f x y having minima maxima have been derived, and the sufficient condition have been discussed with the sign of second order partial derivatives del 2 f over del x square, that is r, and other second order partial derivatives del 2 r over del 2 x y square as t and del 2 f over del x del y as s. Then r t minus s square will govern the sign of minima and maxima. I have also explained the Lagrangian multiplier method, which is used when we want to find minima or maxima of a function of two or more variable with a given condition. Condition may be more than one. I have explained the procedure with example. I hope you have enjoyed the lecture. Thanking you.